settle in for a moment and picture the whole night sky at once. Not just the stars you can see from your window, but every star, every galaxy, every cloud of dust and gas stretching out in every direction. Picture the deep quiet of it, the slow drift of light that has been traveling for millions of years to reach the small, warm room where you are lying down. For a long time, when we looked out at all of this, we looked for patterns in space. We drew lines between stars and called them shapes. We measured the distance between galaxies. We mapped how matter clumps together in vast webs, with long shining threads and dark empty voids between them. Space, we learned, has a structure. It has a texture. It has an order we can trace with our eyes and our instruments. But there is another kind of structure the universe seems to hold. Not a pattern you can see by looking outward across the sky. A pattern you can only see by watching, by waiting, by letting time pass and noticing what returns. Some things in the cosmos repeat. A distant star may brighten and dim on a schedule you could set a clock to. A dead sun spinning in the dark may send out a beam of light every few thousandths of a second, steady as breath. A pair of stars may swing around each other for billions of years, tracing the same slow loop again and again. These are structures that live in time rather than in space. Their shape is a rhythm, one small thing before we drift further out. The universe has a new wonder for you every single night here. If you'd like one waiting each evening, subscribe and let it find you. The deeper you look, the more of these rhythms you find. Comets that swing back into view after centuries away. Moons that lock into gentle dances around their planets. One orbit for every two of another. Whole galaxies that flicker with slow, patient pulses from the giant black holes at their hearts. The universe, it turns out, is not silent. It hums, it ticks, it beats. And here is where the mystery of physics, we thought of time as something that simply passes. A smooth, featureless river carrying everything forward. Space could have shape. Space could bend and curve and form patterns. But time was just the backdrop against which those patterns unfolded. Time itself, we assumed, had no structure of its own. In the last decade or so, some physicists have begun to wonder if that assumption is wrong. There are quantum systems, built carefully in laboratories, that seem to repeat in time, in a way no ordinary clock can. They are called time crystals, and their name is not a metaphor. A normal crystal like salt or quartz is a pattern that repeats in space. Its atoms sit in a grid, over and over in the same arrangement. A time crystal is a pattern that repeats in time. Its state returns over and over in the same rhythm without any outside push driving it. Whether this discovery means something deep about the nature of time itself, or whether it is a small and beautiful quirk of quantum mechanics with no larger meaning, is still an open question. Some researchers think time crystals hint that time has a hidden geometry, a kind of texture we have only just begun to notice. Others suspect they are a curiosity, real and strange, but not a doorway to anything bigger. The debate is quiet and ongoing. Nobody has settled it. That question is what we are going to sit with tonight, not to solve it, just to wonder about it, to let the mind wander through all the ways the cosmos seems to keep time, from the fastest pulsars to the slowest galactic drums, and to hold gently in our thoughts the possibility that time itself might have a shape. For the next few hours, we will drift outward together. We will visit dead stars that spin like lighthouses. We will listen for radio bursts that return from unknown corners of the sky. We will watch shadows cross other suns and imagine tides that rise and fall not in water, but in the fabric of space-time. And we will keep returning to that one soft question. Does the universe merely happen in time, Or is time itself something the universe is built from, layer by rhythmic layer? For now, let your breathing slow. Let the small room around you soften. The cosmos is patient, and so are we. Before we sit with the deeper puzzle of time crystals, it helps to spend a little while with the simplest kind of cosmic clock we know. In the deep dark of space, there are stars that behave like lighthouses. They spin, and as they spin, they sweep beams of radio waves across the sky. Each time a beam passes over Earth, our telescopes hear a soft, precise tick. These stars are called pulsars, and they are the closest thing the universe has to a natural metronome. A pulsar begins its life as an ordinary massive star, many times heavier than our Sun. When such a star runs out of fuel, its core collapses in a matter of seconds. The outer layers blow away in a bright explosion, and what remains is a small, dense sphere called a neutron star. If that neutron star spins quickly and beams out radio waves, we call it a pulsar. So a pulsar is really a certain kind of neutron star, seen from a certain angle, at a certain moment in its long life. The size of these objects is hard to picture. A typical pulsar is only about 20 kilometers across. That is roughly the width of a small city. And yet inside that tiny ball is more mass than the entire Sun. A single sugar cube of pulsar material would weigh about as much as a mountain here on Earth. The matter is packed so tightly that atoms as we know them cannot survive. Instead, neutrons press against neutrons in a state we still do not fully understand. The spin of a pulsar is what makes its heart beat. Some pulsars turn slowly, taking a few seconds for each rotation. Others spin hundreds of times every second, faster than the blades of a kitchen blender. One of the fastest known pulsars completes more than 700 turns in a single second. Try to imagine an object the size of a city, heavier than the Sun. Whirling that quickly, the surface would move at a good fraction of the speed of light, and yet the ticks arrive at our telescopes with a steadiness that rivals the best atomic clocks on Earth. The first pulsar was discovered in 1967 by a young astronomer named Jocelyn Bell Burnell and her team. At first, the signal was so regular that some researchers half-jokingly called it LGM1, short for Little Green Men. They wondered if they were hearing a message. But more pulsars soon appeared in other parts of the sky, and the natural explanation grew stronger. The universe, it turned out, was full of these spinning beacons. Pulsars are usually found within our own galaxy, the Milky Way. Some lie only a few hundred light years from Earth. Others are tens of thousands of light years away, closer to the crowded galactic center. A light year, if it helps, is the distance light travels in a year, a little under 10 trillion kilometers. So even the nearest pulsars are unimaginably far, and yet their ticks reach us so cleanly that we can time them to a fraction of a millionth of a second. Their ages vary widely. A young pulsar, only a few thousand years old, spins quickly and pulses with strong energy. As the millennia pass, it slowly gives up that energy to the space around it. It spins a little slower each year, and its beam grows a little fainter. Some pulsars are hundreds of millions of years old, quietly ticking away long after their birth explosion has faded into diffuse gas. The oldest ones will eventually go dark, though the process takes longer than the age of most civilizations could ever measure. What draws us to pulsars for the purpose of this long night is their rhythm. A pulsar does not repeat in space the way a crystal of salt repeats its pattern of atoms. It repeats in time. Tick, a gap, tick, another gap, tick again. The pattern lives in the sequence of moments rather than in a shape you could hold. and the pattern is astonishingly reliable. Some millisecond pulsars keep time so well that astronomers use networks of them as a kind of cosmic clock, listening for the faint pull of passing gravitational waves. That is the seed of tonight's larger question. If a spinning neutron star can carve such a clean rhythm into the fabric of time, might other things in the universe do something similar, in stranger and quieter ways? Some researchers wonder whether repetition in time might be as fundamental as repetition in space. Others suspect the resemblance is only a helpful comparison, nothing more. For now, the pulsars keep ticking, and we keep listening, and the deeper meaning stays open. Long before there were clocks, there were binaries, two stars, bound together, tracing slow ellipses around a shared center of gravity. This is one of the oldest rhythms in the sky, and one of the first places we learned to see time itself keeping a beat. To understand how such a clockwork comes to exist, we have to travel back to a cold cloud of gas and dust drifting between the stars. These clouds are enormous, hundreds of light years across, and colder than almost anything in the universe. Inside them, tiny grains of frozen matter drift in near silence. For millions of years, nothing much happens. Then something gives the cloud a push. A nearby star explodes. A passing wave of density sweeps through. A shock ripples across the darkness. The cloud begins to fall inward. Gravity, patient and slow, gathers the gas into knots. Each knot spins faster as it shrinks, the way a skater pulls in her arms. Inside these knots, the pressure rises, the temperature climbs, and where the density is highest, the material breaks into pieces rather than forming a single ball. Two centers, sometimes three, begin to grow side by side. This is where the story of a binary star begins, not as two lonely suns that later met, but as siblings born from the same collapsing knot. Most stars in the sky are thought to have formed this way, in pairs or small families, rather than alone. Our own Sunday may once have had a companion, though the evidence remains open and much debated. As the two young stars condense, they inherit the spin of the cloud that made them. They begin to orbit each other, tugged by mutual gravity, spiraling around a point between them. That point is the barycenter, the invisible pivot they both circle. From this early moment, the binary already has a rhythm, a period, a cycle that will last, in some cases, for billions of years. The details of how they settle into that orbit remain uncertain. One idea is that binaries form directly from the fragmentation of the original cloud, with the two stars already tied to one another from birth. Another idea is that some binaries form through capture, when two stars drift close enough for gravity to lock them together. Both processes probably happen. Which one dominates, and under what conditions, is still an open question in astronomy. Once the pair is formed, the clockwork begins in earnest. Kepler's laws, worked out centuries ago from watching planets, applied just as cleanly to two stars in orbit. The closer they are, the faster they move. A tight binary might complete an orbit in a few hours, day. Wide binary might take thousands of years to close a single loop. Every one of these systems is a natural timepiece, ticking at its own pace, set by the mass of the stars and the distance between them. The stability of these clocks is remarkable. A binary system, undisturbed, can keep the same period for longer than the age of the Earth. This is one reason astronomers grew so attached to them. If you want to measure time in the cosmos, you look for something that repeats, and binaries repeat with a quiet, gravitational patience that no earthly clock can match. Yet, Even this clockwork slowly changes. Over vast spans of time, the two stars pull tides in each other's outer layers. Those tides drag on the orbit, transferring energy and shifting the period by tiny amounts. Some binaries slowly draw closer. Others drift apart. A few, in the most extreme cases, spiral inward until they touch, merging into a single star or triggering a violent burst of light. The clock, in the end, is not eternal, it ages. But it ages so slowly that on human timescales it seems perfect. This is the deeper lesson the binaries offered. Repetition in the sky is not the same as sameness. A rhythm can be steady for 1 billion years and still, on some hidden level, be evolving. The beat you hear tonight is not quite the beat that was heard when the first single-celled life stirred in Earth's oceans. It is close enough that we call it the same. It is different enough that given long enough, the difference would matter. When we look at a binary star through a telescope, we see 2 points of light. When we measure their motion over years, we see an ellipse. And when we think about them carefully, we see something stranger. We see a structure that lives not in space alone, but in time. A shape you can only trace by waiting. A pattern that only exists if you are patient enough to watch it turn. There is a certain kind of star that does not simply shine. It breathes slowly, patiently. Over days or weeks, it swells and shrinks, brightens and dims, in a rhythm so steady you could almost set a clock by it. These stars are called Cepheid Variables, and they are among the gentlest metronomes in the sky. To understand what they might tell us about time and its hidden textures, it helps to ask what they are actually made of, and how that inner recipe gives rise to their long, slow pulse. A Cepheid is, at its heart, a very ordinary thing. It is a ball of gas, mostly hydrogen and helium, held together by its own gravity, and lit from within by the fusion of light elements into heavier ones. But somewhere along its life, this star has grown larger and cooler than our own sun. Its outer layers have puffed outward, and its interior has begun to behave in a curious way. A layer of helium, buried beneath the surface, becomes the source of the star's rhythm. The mechanism has a quiet elegance when the helium in that inner layer is doubly ionized, meaning both of its electrons have been stripped away by heat. It becomes opaque, like a dark curtain drawn across the star's inner light. Radiation pushing outward from the core gets trapped behind this curtain. Pressure builds. The star swells. As it swells, the layer cools. The electrons return to the helium atoms, and the curtain grows transparent again. Light streams through. Pressure drops. The star contracts. Then the cycle begins once more. Astronomers call this the Kappa mechanism, and it turns a star into a slow-beating heart. The pulse can last a few days for smaller Cepheids, or many weeks for the largest, and the beauty of it is that the period of the pulse tells you how bright the star truly is. This link between rhythm and luminosity is what lets us measure distances across the universe. A repeating signal in time becomes a ruler in space. The ingredients matter here. Hydrogen and helium make up almost all of the star's mass. The same hydrogen and helium that formed in the first minutes after the beginning of the universe. But scattered through the star are heavier elements: carbon, oxygen, nitrogen, iron. And these did not exist in the early cosmos. They were forged in the cores of earlier stars, stars that lived and died long before the Cepheid was born. When those older stars ended their lives, they scattered their ashes into clouds of gas. From those enriched clouds, new stars condensed, carrying the memory of everything that came before. So when you look at a Cepheid pulsing steadily in a distant galaxy, You are watching a rhythm powered by ingredients that were assembled across billions of years of cosmic history. The iron in the star's atmosphere, the trace metals that shape how it swells and cools, all of it came from earlier generations. The same is true of us. The iron in your blood, the calcium in your bones, the oxygen you breathe. These atoms were once inside stars, and some of them may have moved through Cepheid-like pulsations before being released into the void. There is something worth sitting with here. A Cepheid repeats in time because of the physical properties of its ingredients. Change the mix, add more heavy elements or fewer, and the rhythm shifts. This is a repetition rooted in chemistry, in the leftovers of dead stars. It is a natural thermodynamic beat, one that will eventually fade as the star exhausts its fuel and moves on. That fading is important because it separates a Cepheid from the deeper mystery this episode is circling toward. A pulsing star is a rhythm with a beginning and an end. It is powered by energy flowing outward, and when the fuel runs out, the beat stops. Some researchers see this as the natural pattern for all repeating structures in nature. Others wonder whether there might be another kind of repetition, one that does not need fuel, one that could continue without loss. Whether such a thing truly exists, or exists only in the strange corners of quantum experiments, remains an open question. For tonight, though, it is enough to picture these breathing suns. Somewhere out in the dark, a giant golden star is slowly swelling, its outer layers cooling toward a soft red, its light dimming. Then, over days, it contracts, warms, and grows bright again. It has been doing this for a very long time. It will keep doing this a while longer, and its rhythm carries within it the ashes of every star that ever came before. Somewhere in the quiet dark between the stars, two objects circle one another in a slow, patient dance. One is a small, dense corpse of a star, called a white dwarf. It is the size of the Earth, but holds the mass of the Sun, packed so tightly that a single spoonful would weigh as much as a mountain. The other is a soft, ordinary star, still burning, still swollen with hydrogen. They are locked together by gravity, and they have been circling for a very long time. This kind of pair is called a cataclysmic variable. The name sounds violent, and in a way it is, but the rhythm they keep is long and slow, like a tide that takes decades to turn. Every so often they brighten in the sky, then they fade, then they brighten again. The question that has puzzled watchers for over a century is not only why they do this, but why the timing of their song is so hard to predict. The forces at work here are simple to name and strange to picture. Gravity does most of the shaping. The white dwarf, small and heavy, pulls on the outer skin of its larger companion. The companion star bulges toward the dwarf, drawn out of round, like a drop of water stretched between two fingers. Slowly, gas begins to peel away from the companion and fall inward. It does not fall in a straight line, it spirals. That spiral forms a flat, glowing disk around the white dwarf, called an accretion disk. Imagine a whirlpool made of hot gas, thin and wide, spinning in silence. Friction inside the disk heats the gas to enormous temperatures. The disk glows in soft blues and whites, and it never stops turning. Material creeps inward, layer by layer, until it finally touches the surface of the white dwarf itself. And here the story slows and deepens. Hydrogen piles up on the dwarf's crust. Gravity presses it down. Pressure builds. Heat builds. For years, sometimes tens of thousands of years, nothing seems to happen. The pile grows. The pressure keeps climbing. Then, one quiet moment, the bottom of the pile reaches a point where it can no longer hold itself together, and the whole layer ignites in a runaway burn. The star flares. From far away, it looks as though a new star has appeared in the sky. Ancient watchers gave it a name, nova, meaning new. The nova is not really new. It is only the visible beat of a rhythm that has been building all along. After the flash, the system quiets, the disk reforms. Gas begins to fall again. The clock, if we can call it that, starts once more. Some cataclysmic variables flare on scales of days or weeks. Others take centuries between outbursts. A few may take longer still. And this is where the mystery begins to open. The forces involved, gravity, pressure, magnetic fields, the friction inside the disk, the strength of the companion stellar wind, all interact in ways that are hard to model. One theory holds that the timing is set mostly by how quickly gas piles onto the dwarf. Another suggests that magnetic fields channel the flow, funneling gas along invisible lines and changing the beat in ways that are still poorly understood. Both ideas capture part of the picture. Near closes the case. There is something worth sitting with here as you drift. The rhythm of a cataclysmic variable is not like the tick of a clock. It is closer to the way a heart beats when a person is deeply asleep. Steady in the long view, but never quite the same twice. The gap between one flare and the next can shift. The brightness of each outburst can vary. The pattern is real, and yet it is loose, repeating, but not rigid. That looseness matters, because it hints at something the whole episode is circling. A true clock keeps perfect time. A true crystal in space repeats without variation. But most of the repeating structures we find in the sky are softer than that. They come back again and again, with small differences each time. Whether time itself carries any kind of hidden pattern, the way space carries the lattice of a crystal, is a question no one has answered. The rhythms of cataclysmic variables are not that answer. They are, perhaps, a gentler version of the same question, written in gas and gravity. For now, the two stars keep circling, gas keeps falling, pressure keeps building on the surface of the small, dense dwarf. Somewhere out there, a nova is quietly getting ready to happen, a beat in a song no one has fully learned to read. Somewhere in the quiet dark, two stars are circling each other. From our small blue vantage point, we cannot see them as two. They blur together into a single point of light, but every so often, that point dims, it fades, holds low for a while, then brightens again. One star has slipped in front of the other, casting a shadow across space toward us. This is an eclipsing binary system, and it teaches us something about the patience of shadows. To feel the scale of what is happening, try shrinking it. Imagine one of the stars is a beach ball resting on a table. Its companion might be a tennis ball, or maybe a marble orbiting a few paces away. Now stretch that little scene out until the beach ball becomes the size of an actual star, and the paces between them become millions of miles. The shadow that beach ball casts is not a small dark patch. It is a cone of darkness longer than the distance from Earth to the Sun, and that cone is sweeping slowly through the emptiness, aimed at nothing in particular, until once every few days, or weeks, or years, it happens to point at us. The light we see dip has been traveling for decades, sometimes centuries. A star 400 light years away is showing us a shadow cast 400 years ago. The eclipse we noticed tonight began when people on Earth were still writing with quills. That is the patience these systems demand. They repeat, faithfully, on schedules we can predict to the minute. But each individual dip in brightness carries a message written a very long time ago. Consider the range of periods these systems keep. Some eclipsing binaries complete an orbit in a few hours. Their stars are so close they nearly touch, their surfaces stretched into teardrop shapes by each other's pull. Others take years or decades to swing around once. There is one famous system, Epsilon Aurigae, whose eclipse lasts nearly 2 full years and repeats only every 27. Think of that, a shadow that takes longer to pass than a human childhood, returning only once in a generation. If you tried to watch a single eclipse of Epsilon Aurigae from beginning to end, you would spend more time than most people spend in school. You would watch the light fade over months, sit with the dimmed star through a long twilight, and only slowly see it brighten again. Astronomers who study it inherit the work from those who came before them. One researcher may catch the beginning of an eclipse and never live to see its match. The next generation picks up the observation like a relay baton passed across time. The scale of these systems is hard to hold in the mind. A single one of the stars might be 100 times wider than our sun. If you swapped it into our own solar system, it would swallow Mercury, Venus, Earth, and Mars, and its surface would nearly reach Jupiter. The companion, hidden in its glare, could be a dense little husk no larger than a small country, yet weighing as much as our whole sun. When the small one crosses in front of the giant, it is like a coin passing before a bonfire seen from across a continent. The dimming is subtle. We measure it with instruments that count individual particles of light. And still, in this patient rhythm, we find one of the clearest natural clocks in the sky. Eclipsing binaries keep time. They tick slowly on their own schedules, indifferent to us. Some of them have been ticking since before the first cells on Earth learned how to split. They will keep ticking long after the last human eye closes, for the last time. Their repetition is not in space, where you might walk from one star to another. Their repetition is in time. The same shadow cast again, the same dip in brightness again, the same quiet pattern, again and again, laid down along the axis of duration itself. It is worth sitting with that idea for a moment, a structure that only exists if you watch long enough, a pattern you cannot see in a single snapshot, no matter how sharp the image. You could photograph an eclipsing binary 1,000 times and still miss what it is doing. The shape of it lives in the interval between the pictures. It lives in the return, and in that sense, these systems already whisper something strange, that some of the most real structures in the universe are not things you can point at, but things you have to wait for, things whose whole existence is a rhythm. Float now, in your mind, above the surface of a yellow star. Not our sun exactly, but one very much like it. Below you, the surface churns like a golden ocean brought to a slow simmer. It is not solid, it is not liquid, it is plasma, a fourth state of matter, where atoms have been torn apart into a soup of charged particles that hum with heat and motion. The color is not the flat yellow of a child's drawing. It is a shifting field of orange and gold, granular and grainy, made of countless bright cells, about the size of small countries. Each cell is a rising column of hot plasma. Each one blooms upward, spreads at the top, cools and sinks back down along its darker edges. The whole surface looks like a pot of honey lit from within, forever bubbling in slow motion. Physicists call this granulation. It is the star breathing heat outward from its core. Now let your eye drift to the darker patches. Sunspots. From a distance they look almost black, but that is a trick of contrast. If you could lift a single sunspot out of the star and set it alone in the sky, it would still shine brighter than a full moon. It only looks dark because the plasma around it is hotter and more brilliant. A sunspot is a cooler bruise on the face of the star, a place where the churning has been calmed. The reason it has been calmed is invisible, but it is the heart of our section tonight. Magnetic fields, great looping ropes of magnetism, rise up from beneath the surface, break through, and thread the sunspot like the poles of a bar magnet, buried in the plasma. Where the field is strong, it stiffens the gas. It holds back the rising heat. The surface there cools by 1,000 degrees or more, and a dark island forms in the golden sea. Around each spot, you would see a delicate fringe called the penumbra. Under close view, the penumbra shows fine filaments arranged like the petals of a dark flower, or like iron filings sprinkled around a magnet. In the very center sits the umbra, the darkest core, sometimes wide enough to swallow the whole Earth without touching its sides. Some sunspots grow larger still, into complex groups that sprawl across regions many times the diameter of our planet. Here is where the rhythm begins to reveal itself. Sunspots do not simply appear at random. They come and go in a slow, patient cycle that lasts roughly 11 years on our own sun. At the quiet part of the cycle, the surface is almost bare, a smooth golden field with only a few small blemishes. Then, year by year, the spots return. They begin at higher latitudes on the star, then drift toward the equator as the cycle matures. At the peak, dozens of spots may freckle the surface at once. Then the cycle winds down, and the star grows quiet again. Something even stranger happens at the end of each cycle. The star's overall magnetic field flips. North becomes south. South becomes north. It takes 2 full sunspot cycles, about 22 years, for the magnetism to return to where it began. So the star is not just repeating in time, it is repeating in a nested way. One rhythm folded inside a longer rhythm. Why does the cycle last 11 years and not 5 or 50? Here the honest answer is that we do not fully know. One idea points to a slow churning motion of plasma deep inside the star, called the dynamo, which winds magnetic fields around itself, the way you might wind thread around a spool. Once the tension grows large enough, the field surges upward and breaks the surface as sunspots. A competing view suggests that flows near the poles, drifting slowly toward the equator, set the pace instead. Both ideas capture pieces of what we see, and neither one predicts every detail. The cycle has skipped beats in the past. During one long stretch in the 17th century, sunspots nearly vanished for decades, and no one is sure exactly why. So imagine the surface again. The golden granulation, the dark islands with their petaled fringes, the invisible magnetic ropes rising and falling in a great unseen weave. And imagine that this whole vast face, larger than 1,000,000 Earths could tile across, is quietly keeping time. It is a clock made of fire, ticking in decades rather than seconds, folded inside a longer clock that ticks in decades of decades. A star, it seems, is a structure that repeats in time as much as it exists in space, and the question of what sets that repetition is still softly open. Our own sun keeps a rhythm we have learned to recognize. Its sunspot cycle rises and falls across roughly 11 years, and its magnetic poles flip in a slower beat of about 22 years. These numbers feel almost tidy, almost designed. Yet when we look outward at other stars that seem to be twins of our sun, the picture grows stranger. Some of them pulse in cycles that match ours closely. Others beat to a rhythm so different that we cannot yet say why. A solar twin, in the simple sense, is a star with merely the same mass, temperature, and age as our sun. On paper, They should behave the way our sun behaves. They should heat their surfaces to the same yellow glow. They should spin at roughly the same rate. They should sprinkle their faces with dark spots that come and go on a familiar schedule. And yet the observations, gathered patiently across decades of quiet telescope work, tell a more layered story. Some solar twins show cycles of only a few years. Quick and shallow others show cycles that stretch far longer than ours, deep and slow, like a bell rung underwater. A few show almost no cycle at all. They sit in long, flat stretches of low activity, as though they have paused their inner clock entirely. Researchers call these quiet stretches grand minima, and our own sun seems to have entered one during the 17th century, a period known as the Maunder minimum, when sunspots became rare for decades. The question that lingers beneath all this is a quiet one. If a star nearly identical to our sun can beat to a different rhythm, then what exactly sets the rhythm in the first place? What lies beneath the surface, deep in the churning layers we cannot see, that decides how often a star will pulse? One theory points to the dynamo. Deep inside a sun-like star, hot plasma moves in vast rolling currents, and those currents twist and stretch magnetic fields. The fields tangle, break, and reform in a slow braided dance. The 11-year cycle in this picture comes from the time it takes for the tangling and untangling to complete. One full loop. Small differences in rotation speed or in the depth of the churning layer could easily stretch or shorten that loop. A twin star spinning slightly faster or with a slightly deeper convective zone might sing at a different pitch. Another theory suggests the story is more chaotic than that. In this view, the cycle is not a clean loop, but a rough approximation, a kind of average behavior that hides many smaller competing rhythms. The star does not truly repeat. It only appears to repeat because we are watching from far away, smoothing out the noise. If this is right, then two twin stars could easily drift into different patterns simply because their internal turbulence took different paths. Both ideas remain open. Neither has been ruled out, and neither has been fully confirmed. The data we have covers only a few decades for most stars, which is barely long enough to catch 2 or 3 cycles. To truly know whether a distant sun keeps a steady beat, we would need centuries of continuous watching. We do not have that yet. We are only beginning. The mystery deepens when we consider what a repeating stellar cycle even means on the surface. It looks like a structure in time. The star returns, again and again, to a similar magnetic state. But the atoms are not the same atoms. The plasma has moved on. Only the pattern remains. In that sense, the cycle is a shape drawn, not in matter, but in duration itself, a form that exists because time keeps passing through it. This raises a soft, strange thought. If a sun-like star can hold a rhythm across billions of years, and if that rhythm is a kind of structure in time rather than space, then perhaps such structures are more common in the universe than we realized. Perhaps every star carries its own quiet time shape, unique as a fingerprint, and perhaps some of those shapes are stable, while others slowly drift, or slip into silence for a while, or wake up again after a long rest. We do not know why our sun keeps the rhythm it keeps. We do not know whether it will always keep it, or whether one day it will fall into another grand minimum, or shift into a slower song entirely. The depths of a star, even a familiar one, remain hidden from us. What we see is only the surface, and even the surface tells us that time itself, in these places, has a texture we are still learning to read. Somewhere in the quiet reaches of the sky, a signal arrives. It lasts only 1,000th of a second, or perhaps a little less. In that brief moment, it carries the energy of the sun across many days, all packed into a single flash of radio light. Then it is gone. For years, we did not know what to make of these flashes. We still do not entirely. And the deepest puzzle of all is that some of them come back. Astronomers call them fast radio bursts. The first one was noticed in old telescope data from 2007, a strange spike that seemed too bright and too brief to be anything ordinary. For a while, some researchers wondered if it was a mistake in the instruments. Then more were found, then hundreds, then thousands. They come from far outside our galaxy, from distances so great that the light we catch tonight left its source long before humans learned to write. Most of these bursts flash once and never repeat. They arrive, they surprise the telescope, and they vanish into the silence of the sky. But a small fraction of them do something stranger. They return. The same patch of sky, the same faint fingerprint in the radio spectrum, sends out burst after burst, sometimes hundreds of them, sometimes with long dry pauses in between. And within a few of these repeating sources, patient watchers have found something even more curious. A rhythm, a cycle. One well-studied repeater seems to grow active every 16 days or so, sending out bursts for a stretch, then falling quiet, then waking again. Another repeater appears to follow a much longer cycle of about 157 days. The counts are still being refined, and not every astronomer agrees the patterns are truly stable. Yet the hint of a schedule is there, tucked into the noise, teasing us to explain it. No one knows what makes them. That is the plain truth. We have theories, and we have arguments, and we have a great deal of careful observing still to do. One idea is that a fast radio burst comes from a magnetar, a young neutron star with a magnetic field so strong it would tear an ordinary atom apart. Something in the crust of the star cracks, or something in its magnetic field snaps and rearranges, and a pulse of radio light escapes. This idea gained ground when a magnetar inside our own galaxy released a burst that looked, in miniature, like the ones from far away. It was the closest thing to a smoking clue we have found. But a single clue is not a full answer. Some researchers wonder whether every fast radio burst really comes from a magnetar, or only some of them. Others propose that the repeating ones involve two objects, not one. Perhaps a neutron star swings around a massive companion in a long, slow orbit, and only when the geometry lines up just so can we see its bursts. That could explain why the signals seem to come and go on a schedule. Or perhaps the neutron star is precessing, wobbling on its axis like a spinning top, so its beam sweeps across us only during certain windows. Or perhaps a dense cloud of gas surrounds the source, and the bursts only escape when the cloud thins. There are stranger ideas too, held loosely at the far edge of speculation. Some have wondered about starquakes on exotic compact objects we have not yet named. Others have asked whether some bursts might involve physics we simply do not have on our chalkboards yet. Every one of these ideas remains open. None has been ruled out, none has been proven. What draws the mind on a night like this is the fact of the return itself. Something out there, unimaginably far, is keeping time. Not the time of a single ticking pulsar, steady as breath. This is time of a different flavor, a rhythm with gaps in it, a pulse with silences, a schedule woven from bursts and stillness, repeating on scales of days and weeks and months. If you sat on a hillside long enough, you would not see them with your eyes. They live in radio waves, not visible light. But the sky above you, right now, is being crossed by these signals, arriving from galaxies whose names we have not yet given. Some are one and done. Some are patient repeaters, waiting for their next chapter. Somewhere among them, perhaps, is a rhythm we have not yet noticed, playing across years we have not yet watched. The question of what keeps that rhythm remains open, and the sky, as always, keeps its own counsel. Not far from the ordinary neutron stars we spoke of earlier, in the same crowded family of stellar corpses, there lives a stranger cousin. We call it a magnetar. It is a neutron star like the others, small and dense and spinning, but wrapped in a magnetic field so strong that no experiment on Earth can come close to matching it. If you could hold one in your hand, which of course you never could, its magnetic pull would rearrange the atoms in your body from a great distance. And yet, for all their power, magnetars keep their own kind of rhythm. That rhythm is one of the quieter puzzles in the sky. A magnetar spins, and as it spins, it sends out pulses. Some are gentle and regular, much like a normal pulsar, ticking every few seconds. Others are sudden and bright, short bursts of X-rays and gamma rays that flare up without warning and then fade. Between these two behaviors lies a whole spectrum of activity that no one has fully mapped. A magnetar can be quiet for years, then wake up for a few weeks of restless flickering, then fall silent again. The pattern is there. The pattern is also not quite a pattern. This is what makes magnetars fit so well into our slow conversation about things that repeat in time. They repeat, but their repetition is uncertain. It has structure at some scales and chaos at others. A magnetar might pulse steadily on the time scale of seconds, drift slowly on the time scale of years, and burst unpredictably on the time scale of decades. 3 clocks running at once, inside one small object no wider than a city. The forces behind these rhythms are still being worked out. One idea is that the magnetar's crust, a shell of crystalline matter, thinner than a mile, sometimes cracks under the strain of its own magnetic field. Each crack releases energy, like a starquake, and that energy escapes as a burst of radiation. In this picture, the repeating flares are the sound of a solid surface groaning against forces it cannot hold. Another idea places the action higher up, in the twisted magnetic field itself, where lines of force snap and reconnect the way they do on our own sun, only far more violently. Both pictures might be partly right. The evidence is still incomplete. What draws us here on this slow night is not the violence, but the timing. Some magnetars have been observed to shift their pulse period, suddenly speeding up or slowing down in an instant. These are called glitches and anti-glitches, and no one is entirely sure what causes them. They suggest that deep inside the star, something is moving. Something is rearranging itself in ways that quietly change the beat of the whole object. A clock that adjusts itself for reasons we cannot yet see. Magnetars also sit near another mystery we have already touched on. Some of the fast radio bursts that flicker across the sky have been traced back to magnetars in our own galaxy. This was a surprise. It means that at least some of these strange, brief signals from far away might come from these odd, magnetic neighbors. But not all fast radio bursts fit that story. The repeating ones, especially the ones with steady windows of activity, may need a different explanation entirely. So, the magnetar is a neighbor, a suspect, and a piece of the puzzle, but perhaps not the whole answer. There is something quietly beautiful about how these objects live in a middle zone. They are not as tidy as pulsars, which tick with almost inhuman regularity. They are not as chaotic as a supernova, which happens once and is gone. They are somewhere in between. They keep time, but their time-keeping wanders. They repeat, but the shape of the repetition slips through our fingers. If time itself has a texture, as some of the ideas we will visit later suggest, then Magnetars may be one of the places where that texture becomes visible on a grand scale. Not a perfect crystal in time, but something rougher and more organic, closer to a heartbeat than a metronome. Whether that difference matters, whether irregular repetition points to the same deep principle as the precise repetition of a quantum time crystal, is not yet clear. Some researchers think the two are entirely separate stories, one about clean symmetry and one about messy astrophysics. Others suspect there may be a hidden thread connecting them. For now, the magnetar goes on spinning, waiting, occasionally flaring, then falling quiet again. Somewhere in that uneven rhythm, something is being kept. We just do not yet know what. Somewhere out in the deep dark, signals arrive that seem to keep a schedule, and no one can say for certain what is sending them. These are the strange ones, the signals that repeat with a rhythm so precise or so odd that our best models begin to strain. They sit at the far edge of what we understand, and they are the reason many astronomers stay curious well past midnight. Consider a source in a distant galaxy known simply by a string of numbers and letters. It sends out bursts of radio energy, and for a long time it was thought that such bursts came only once, flashing briefly and then falling silent forever. Then one source repeated, and another, and then one began to repeat on a schedule, sending its flashes in a window that returned every 16 days or so. Inside that window, the bursts came and went. Outside of it, silence. No one knows why. One idea is that the source sits in a binary system, where a compact object with a magnetic field is orbiting a larger companion. As it swings around, its beam of radio energy sweeps toward us for a few days at a time. Another idea points to a slow, wobbling neutron star, turning like a top that has almost, but not quite, fallen over. A third suggests that the surrounding gas itself opens and closes windows in the signal, letting some bursts through and blocking others. Each theory fits some of the data. None fits all of it. Then there are the sources that repeat far more slowly. In recent years, astronomers found a signal that pulses once every 18 minutes, another once every 21 minutes. These periods are far too long for a normal pulsar, which usually spins many times a second. A neutron star, turning that slowly, should not be able to shine at all, at least not by the rules we currently use. Yet the signals arrive, patient and steady, from somewhere in our own galaxy. One possibility is that these are magnetars that have aged in strange ways, holding on to enough magnetic power to still glow despite their slow rotation. A competing view is that they are white dwarfs, dense, dim stellar cores about the size of Earth, with unusually strong magnetic fields. A third suggestion is that they represent a kind of object we have not properly named yet, sitting in a gap between the categories we know. The evidence is thin, and the debate is quiet, and no side has won. Even stranger are the signals that seem to shift their rhythm over time. Some repeating sources speed up, some slow down, some skip a beat, fall silent for months, and then return exactly on schedule, as if they had never left. A few appear to change the shape of their pulses from one cycle to the next, as though the source itself were rearranging. There is one signal discovered decades ago that lasted only 72 seconds and never returned. It was so unusual, so sharp, and so structured that it earned a nickname among the researchers who studied it. Careful searchers of the same patch of sky, night after night, have found nothing. It may have been a one-time event. It may have been a repeater, with a period longer than the entire span of our observations. We cannot yet tell the difference, and we may not be able to for a very long time. The extremes push at our definitions. If a pulse repeats every millisecond, we call it a pulsar. If it repeats every few seconds, we call it something else. If it repeats every 18 minutes, we do not have a comfortable name, and if the period is so long that we have not lived long enough to see the second pulse, the source might look, to us, like a single unexplained flash in the sky. This is where the question of time crystals drifts back into the conversation. In a laboratory, physicists have made small quantum systems that repeat in time on their own, without being driven at that rhythm. Out in the cosmos, we see repeating signals whose rhythms we cannot yet match to any known driver. There is no reason to think these two things are related. And yet, the pattern is the same at heart. Something is keeping a beat, and we do not fully understand the metronome. Perhaps every unexplained repeater will one day resolve into a known object with familiar physics. Perhaps some will not. Perhaps a few will point toward states of matter we have not yet imagined. Quiet clocks in the dark, ticking to a rule we have not yet written down. For now, they continue to arrive, faint and faithful, waiting for us to listen more carefully. Far from the loud engines of pulsars and the sudden flares of distant stars, there is a quieter kind of rhythm. It hides in the movements of moons around the great planets of our own solar system. Small worlds trace slow paths, and some of them keep a strange, patient beat with one another. The pattern is called orbital resonance. It is one of the softest examples of time repeating in the cosmos, and it is easy to miss. Look toward Jupiter. 4 large moons circle it, and 3 of them share a quiet secret. Io, the innermost of these 3, finishes 4 laps around the planet in the time it takes Europa to finish 2. In that same span, Ganymede completes just 1. 4, 2, 1. The ratio is nearly perfect. It has held for a very long time. Each time Io swings past Europa on the inside track, it does so at almost the same spot in its orbit. Each time Europa passes Ganymede, the meeting point drifts only a little. The 3 moons trade tiny nudges of gravity, back and forth, and those nudges lock them into step. This is called a Laplace resonance, named after the mathematician who first described the pattern. What makes it beautiful is how gentle the mechanism is. There is no cable, no gear, no engine, only gravity, pulling with a soft and steady hand across empty space. The moons could, in theory, drift into any rhythm at all. Instead, they settled here, into a chord that has held for millions of years. The resonance does more than mark time. It shapes the moons themselves. Because Io keeps meeting Europa at the same phase of its orbit, its path is pulled slightly out of round. That small stretch, repeated on every lap, squeezes the moon from the inside. The rock heats up. Volcanoes bloom on Io's yellow surface, glowing with sulfur and molten stone, painting the little world in shades of gold and orange and pale green. Europa feels a softer version of the same squeeze, and beneath its cracked white shell of ice, a hidden ocean may be kept warm by nothing more than the timing of an orbit. That is the quiet miracle here. A repeating pattern in time becomes a source of heat. A rhythm becomes an energy somewhere under Europa's frozen crust. Water may be sloshing in slow tides, warmed by a beat that has been steady since before the first fish swam in Earth's seas. Saturn holds its own resonances, softer and stranger. Mimas and Tethys keep a 2-to-1 rhythm. Titan and Hyperion keep a 4-to-3. Small moons herd the icy particles of the rings, tugging them into sharp edges and narrow gaps. The Cassini division, That dark stripe you can see with a backyard telescope is carved by a resonance with Mimas. Every particle that tries to settle in that gap gets nudged gently at the same point in every orbit until it drifts away. A shadow in the rings is really a rhythm made visible. Pluto and Neptune keep an even slower duet. For every 3 orbits Neptune completes around the Sun, Pluto completes too. Their paths cross on paper, but because of the resonance, they never come close in space. The timing keeps them safe from one another. It has done so for perhaps 4 billion years. What scientists still wonder about is how these patterns settled in the first place. One idea is that moons formed near their resonances and simply stayed. Another idea is that they wandered inward or outward over long ages, sweeping through many possible rhythms, and were caught by the strongest ones, like a needle finding a groove. The evidence favors the wandering picture, but the details are not fully worked out. Some resonances may be young, some may be slowly falling apart. We do not yet know which are stable forever, and which are only pausing on their way to something new. There is a thought that lingers here, a time crystal. In the laboratory is a quantum system that ticks in a steady beat, without any driving clock behind it. An orbital resonance is not a time crystal in the strict sense. It is powered by gravity, and it can, over billions of years, drift. Yet, both are examples of nature choosing a repeating rhythm when nothing forces it to. Both are patterns in time rather than in space. Whether the resemblance is deep or only surface, no one can say. For tonight, it is enough to picture Io swinging past Europa, and Europa passing Ganymede, and the whole arrangement humming along like a slow music box wound by nothing at all, a quiet chord played in orbits, still ringing. Long before anyone spoke of time crystals or pulsars, before radio dishes turned their faces to the sky, humans watched the heavens and noticed something odd. Now and then, a strange bright object would appear among the stars. It would grow a tail, drift across the sky for weeks, and then fade away. For most of human history, these visitors seemed to arrive without pattern. They were called comets, and they were treated as one-time events, singular and unrepeating. The idea that a comet might return, that it might be a structure in time rather than a single moment, took centuries to form. Ancient observers in China kept careful records of every bright comet they saw, sometimes noting the exact night, the direction of the tail, the color of the glow. These records stretch back more than 2,000 years. Yet no one connected the entries across generations. Each comet was thought to be new, born fresh from some unknown place, never to be seen again. The shift began slowly, and it began with mathematics. In the late 17th century, an English astronomer named Edmund Halley grew fascinated by the comet records of his time. He gathered every reliable observation he could find. He compared the paths of comets seen in 1531, in 1607, and in 1682. The numbers matched the same slow curve, the same direction of travel, the same tilt against the plane of the planets. Halley proposed something quiet and radical. These were not 3 comets. They were one comet. Returning, he predicted it would come back around 1758. He did not live to see it. But on Christmas night of that year, a German farmer and amateur astronomer named Johann Palitz spotted a faint smudge low in the sky, and the comet arrived roughly on schedule. It was the first time humans had ever confirmed that something in the sky repeated in time on a scale longer than a human life. That single discovery changed the way people thought about the heavens. The sky was no longer just a place of static patterns and rare surprises. It contained hidden rhythms, cycles too long for any one observer to notice. structures that unfolded across generations. The comet Halley studied returns every 75 or 76 years, tracing a long, thin loop that carries it out past the orbit of Neptune and back again. To understand it, you had to think in centuries. Other comets were slowly added to the list. Some had shorter cycles, returning every few years. Others had cycles so long that no human had ever watched one complete a loop, and never would. Astronomers began to imagine a vast reservoir of icy bodies, far beyond the planets, drifting in the cold dark, occasionally nudged inward to make their long, slow visits. The names for these regions came much later, but the idea was rooted in the discovery that comets keep time. The instruments used were modest by our standards: a quadrant for measuring angles, a small telescope with a hand-ground lens, a notebook, a candle. The real instrument was patience, passed from one generation to the next. A prediction made by one astronomer could only be tested by someone not yet born. This is the peculiar shape of studying things that repeat in time. You must trust the record. You must trust that others will keep watching after you are gone. Mistakes were common. Some early astronomers thought comets were events in the atmosphere, whether of a strange kind, not distant travelers at all. Others assigned them meanings they could not carry, treating each appearance as a message. The slow correction of these ideas came not from any single genius, but from the steady accumulation of careful measurements over decades. Errors in the predicted return of Halley's comet, off by a year or more in early calculations, were slowly refined as the pull of Jupiter and Saturn on the comet's path was better understood. What the comet hunters gave us, without quite meaning to, was a new idea. The sky contains patterns that live in time. A structure need not be a shape you can see all at once. It can be a rhythm, a return, a signal that only reveals itself if you wait long enough and remember well enough. This same habit of mind, born from tracking icy visitors across generations, would later let astronomers recognize the beat of pulsars, the breathing of variable stars, and eventually the strange quantum repetitions we now call time crystals. Whether time itself has a deeper structure remains an open question, but the first small proof that time carried structure at all came from a farmer looking up on Christmas night, seeing a promised light return. Out among the wandering worlds, something quietly strange is happening. Planets do not simply orbit their stars in neat, unchanging loops. They wobble, they tilt, they shift in ways that repeat, but not always in the way we would expect. And within these small motions hides a surprise that even seasoned astronomers find beautiful and a little unsettling. Consider a planet moving around a distant star. From far away, the star itself seems fixed, a steady point of light, but that star is also moving, pulled gently by the planet it holds. Every world tugs on its parent sun, and the sun answers with a tiny wobble of its own. This small dance repeats in time. It has a period, a rhythm, a return, and by watching this rhythm we discovered most of the planets we now know about beyond our own solar system. Here is the first surprise. The stars themselves are the ones that give the planets away. We rarely see the planets directly. Instead, we watch the star wiggle back and forth, or dim slightly as a world passes in front. The whole practice of finding new worlds is really the practice of listening for repeating signals in time. Planets are silent partners. Their stars are the ones humming their names. The wobbles hide another oddity. Some planets travel in orbits so tilted that they seem to defy the tidy picture of a flat, disc-shaped solar system. There are worlds that circle their stars sideways, as if turned on their edge. There are even worlds that move backward, against the spin of the star they belong to. How they arrived at such angles is still an open question. One idea is that other, unseen planets nudged them into those strange paths long ago. Another suggests that passing stars or interactions inside the birth cloud tilted them early. Both possibilities remain on the table. Then there is the wobble within the wobble. A single star with a single planet gives a clean, repeating signal. But when several planets share a star, their signals overlap. The star traces a small, complicated curve in space, layered from many rhythms at once. Astronomers must untangle these braided pulses like listeners, picking out separate instruments in a quiet piece of music. Sometimes a hidden world announces itself only through a slight extra beat in the pattern, a rhythm inside the rhythm that nothing else can explain. Some planets do something stranger still. Their orbits shift over long stretches of time, drifting slowly like the hands of a very patient clock. The whole shape of the orbit turns. In our own system, tiny drifts of this kind happen to Mercury, and figuring out its motion once helped confirm the bending of space by gravity. Out in other systems, similar drifts are being watched with care. Each drift is itself a repeating pattern, a rhythm layered on top of the shorter yearly cycle. Here is a detail that many people find hard to believe. A planet does not need to be near its star to reveal itself through timing. Some worlds have been found around dead stars, around the tiny cores left behind after a sun collapses. These cores can spin hundreds of times per second, and their pulses are so steady that even a small planet in orbit shows up as a faint hiccup in the beat. The first planets ever found beyond our sun were discovered this way, circling the ashes of a dead star. That, in its own way, is one of the quiet surprises of modern astronomy. The first alien worlds we ever confirmed were orbiting a corpse, and there are wandering worlds that have no star at all. Rogue planets drift alone through the dark, between suns, carrying no yearly rhythm, no repeating pulse of light. They may still spin, they may still hold moons. Some may even keep warm oceans beneath ice, warmed by the slow decay of elements deep inside. But their time signature, if they have one, is invisible to us. We can only guess how many of them there are. Some studies suggest there may be more rogue planets in our galaxy than stars. The estimate is uncertain and hotly debated. What ties all of these surprises together is a single, quiet idea. The wobble of a wandering world is a repeating structure in time. It is not a shape you can hold. It is a return, a coming back, a promise the planet makes to its star, and to anyone patient enough to listen. Whether the deeper meaning of such rhythms points to something profound, or simply to the mechanics of gravity playing out, remains an open and beautiful question for another quiet night. Tides are one of the oldest rhythms we know. The moon pulls on the ocean, and the water rises and falls in a slow, steady beat. Twice a day, the sea breathes in and out along the coast. This rhythm is not stored in the water itself. It lives in the relationship between the moon, the earth, and the sun. A tide is a pattern that repeats in time, because two bodies keep moving in a certain way with respect to each other. That is a useful picture to hold as we sit with the mystery of structures that repeat in time. A tide is not really a thing you can point to yet. It is a shape carried by matter, drawn out by gravity, painted onto the ocean night after night. If the moon stopped orbiting, the tide would fade. The rhythm depends on the dance. Many of the repeating patterns in space work this way. Pulsars beam only seems to blink because the star spins. An eclipsing binary only dims because two stars keep circling each other. The rhythm is not stored in the light. It is stored in the geometry of moving things. In a sense, all of these are tides. They are patterns pulled through time by the steady motion of masses. The sun tugs on Earth too, and the two tugs together shape the tides we see. When the sun and moon line up, tides run higher. When they pull at right angles, tides run softer. So even the ocean's simple rhythm is really two rhythms braided together, cycles within cycles. This is a common shape in nature. A short beat sits inside a longer one, and that one sits inside another still. Volcanoes offer a different kind of connection. When a large eruption throws ash and sulfur into the upper air, sunlight dims for a season or two. The planet cools a little. Then the haze clears and warmth returns. That is a slow pulse, uneven and hard to predict, but it is still a repeating pattern of a kind. The Earth itself keeps a rough time by the shocks it gives itself. Galaxies do something similar on a scale that is hard to hold in the mind. One galaxy passing near another can stir long tides of stars. Ribbons of light stretch out across empty space and slowly wrap back in. If you could watch for hundreds of millions of years, you would see a rhythm, a slow braided pattern, rising and falling, as two great islands of stars pull on each other. The same word, tide, fits here, though the water is made of suns. This is where the puzzle of time crystals begins to feel less strange. A time crystal in the lab is a tiny quantum system that falls into a repeating pattern all on its own. It ticks, in a sense, without being wound. One view is that this is just a subtle new kind of matter, closer to a clever oscillator than to anything deep. Another view is that it belongs to the same family as tides and orbits and spinning stars, a pattern carried by relationships, not stored in any single piece. The difference, if there is one, may lie in what supports the rhythm. A tide needs the moon, a pulsar needs its spin, a binary star needs its partner. Take away the other body, and the beat fades. A time crystal seems to keep its beat without needing anything outside it in the same way. Some researchers wonder if that means time itself is playing the role that the moon plays for the ocean, that the ticking rides on a hidden structure in time, the way a tide rides on gravity. Others think this is reading too much into a quiet laboratory effect. Both views can sit together for now. What we can say is that the universe is full of rhythms that arise from connection. A single star, alone in the void, would not blink. A single moon with nothing to orbit would not raise tides. The music of the cosmos comes from things playing off one another, gently, across huge distances and long stretches of time. That may be the quiet lesson of this whole story. Repetition in time is almost never a solo. It is a duet, or a chorus, or an orchestra of masses and fields, all leaning on each other. Somewhere in that chorus, the time crystal sings its odd little note, and no one yet knows whether it is only a soft harmony inside the larger song, or a hint that time itself has a shape we have not learned to hear. Tonight, both possibilities can rest side by side. Something changes when a large mass moves through space. The fabric around it bends, and if the mass moves in the right way, that bending sends out a ripple. These ripples are gravitational waves. They travel outward at the speed of light, stretching and squeezing everything they pass through by amounts smaller than the width of a proton. For a long time we could only guess they existed. Now we can hear them. The instruments that catch these waves are long tunnels lined with mirrors. Sitting quietly in remote parts of the world, they listen for the faintest tremor in the distance between 2 points, and what they hear, more often than not, is a rhythm. 2 dense objects, locked in orbit, spiraling slowly toward each other, each loop shorter than the last, each loop sending out a wave. The signal rises in pitch as the orbit tightens, ending in a chirp that lasts less than a second, but carries the memory of millions of years. That chirp is a kind of clock. It repeats. It changes as it repeats. And that gentle change tells us something new about how time and rhythm move together across the cosmos. Some of these waves come from pairs of neutron stars. Some come from black holes. Some come from mixtures of the two. Each pair carries its own tempo, set by mass and distance and the geometry of the orbit. If you could listen to a full sky of these waves at once, you would not hear silence. You would hear a slow, layered hum, made of countless orbits at countless speeds. The universe, in this sense, is quietly ringing all the time. There is a longer, slower version of this rhythm too. Some of the largest black holes in the universe sit at the centers of galaxies, and when galaxies merge, their central black holes drift toward each other. They can spend millions of years spiraling together, sending out gravitational waves with periods measured in years. To catch waves that slow, we need a different kind of listener. So astronomers have turned to pulsars. They watch the timing of dozens of pulsars scattered across the sky, looking for tiny shared shifts in when their pulses arrive. If a gravitational wave passes through the galaxy, those pulses should ripple in a coordinated way. Recent measurements suggest that this hum is really there. The pulsar timing arrays have found a faint, low background signal that seems consistent with a chorus of distant supermassive black holes, all singing at once, but the interpretation is still open. One idea is that the signal comes from these orbiting giants. Another idea is that it comes from processes in the very early universe, when space itself was young and violent. The signal we are hearing may be a blend of both, and researchers are still working to separate the voices. What matters for our story is that gravitational waves give us a new kind of metronome, not one that stays fixed, but one that shifts. The pitch rises, the wavelength stretches. The universe itself is expanding, and that expansion pulls the crests of these waves apart as they travel. A wave, born 1 billion years ago, arrives lower in pitch than the one it was when it left. In this way, cosmic rhythm carries the fingerprint of cosmic change. Some researchers wonder if these rhythms can be used to test the deepest ideas about time. If time has a hidden structure, as certain quantum experiments hint, then perhaps gravitational waves are the largest expression of that structure. Perhaps every ripple is a note in a much older song. Others push back, pointing out that a wave is not a crystal, and that a passing ripple is very different from a system that repeats without any push from outside. The comparison is tempting, but it may only be a comparison. Still, when you sit with the idea, something quiet settles in. The universe is full of clocks that change as they tick. A pair of black holes orbits a little faster each year. A pulsar spins a little slower each century. Space itself is stretching, and the sound of that stretching is folded into every wave that crosses it. Nothing here is truly constant. The rhythm is always drifting. We do not yet know what the full chorus sounds like. We do not yet know whether the background hum comes from many sources or from something stranger. We do not yet know whether these rhythms connect, at some deep level, to the periodic textures we find in quantum systems. What we do know is that the sky is not silent. It has been humming all along, and only now are we beginning to learn how to listen. When a black hole forms, or when two of them meet and merge into one, the newborn object does not simply settle into silence. For a brief moment, it trembles, it rings, the way a bell rings after it is struck. The surface we call the event horizon, that dark boundary past which nothing returns, quivers with a set of tones that physicists call ring-down modes. These are ripples in the shape of space-time itself, and they carry away energy in the form of gravitational waves until the black hole grows still. We cannot see this ringing with our eyes. Black holes give off no light of their own. Their surfaces are darker than any dark you have ever seen, darker than the deep ocean, darker than a cave sealed off from the sun for 1,000,000 years, and yet the ringing is a kind of light. In the broadest sense, it is a signal. It is a pattern moving outward through the fabric of the universe, and it repeats in time with a rhythm that depends only on the black hole's mass and spin. Each tone fades quickly. The ring lasts only a fraction of a second for the black holes we have detected so far. But within that fraction of a second, the wave rises and falls in a repeating pattern, again and again, softening as it goes. Scientists call this a damped oscillation. Imagine tapping a wine glass and hearing the note gently die away. The black hole does something similar, only the note is not sound. It is the shape of space, stretching and squeezing as the wave passes through. Here, the mystery grows quiet and deep. In theory, the ring-down tones should follow a precise pattern, predicted by our current understanding of gravity. If we measure the tones carefully, we can test whether that understanding is complete. Some researchers wonder whether the ringing might contain small, extra notes, faint overtones, that would hint at new physics near the event horizon. Others suspect the ring will match the standard prediction exactly, leaving no room for surprises. The observations so far are consistent with the simple picture, but the signals are faint, and the question remains open. There is a stranger possibility as well. Yea, a few theorists have asked whether black holes might not be quite what we think they are. Perhaps their surfaces are not perfectly smooth. Perhaps they have some soft, fuzzy structure just above the horizon, made of exotic matter or quantum threads. If that were true, then a wave falling in might partly bounce back. The ring down would then show faint echoes, repeating pulses of gravitational light arriving after the main ring, spaced by tiny intervals of time. A handful of studies have hinted at such echoes in the data, but most careful reviews have found the hints too weak to trust. The competing view is that the echoes are simply noise, patterns our eyes want to see in a sea of static. If echoes are real, they would repeat in time in a way no ordinary object does. They would be a kind of temporal structure written into the aftermath of a cosmic collision, a signature of something we do not yet understand about the edge of a black hole. If echoes are not real, then the ring down is a cleaner kind of temporal pattern, a pure damped tone whose repetition tells us that gravity behaves just as predicted, even in the most extreme place we know. Picture the scene as it might look if we could translate it into light. Two dark spheres spiral together in a slow, silent dance. The space around them shimmers. When they touch, a burst of energy flares outward, invisible to eyes, but carried by the trembling of space-time. The newborn black hole quivers, its horizon flexing in and out along different axes, each quiver a note in a fading chord. The chord repeats, softer and softer, until the black hole becomes perfectly smooth and perfectly still. Then there is only the dark sphere, and around it the empty patience of the universe. We have heard a few of these rings now, through detectors so sensitive they can measure a change in length smaller than the width of an atomic nucleus, across kilometers of tunnel. Each one is a repeating structure in time, born from the merger of two of the strangest objects in existence. Each one lasts less than a heartbeat, and each one carries a question we have not fully answered, whether the ringing tells us only about gravity, or whether it also whispers something about the hidden edge of what we call a black hole. For now the whisper is soft, and the interpretation stays open, and the dark spheres keep their secrets. Deep in the hearts of certain star systems, something strange happens to the light. It does not simply glow, it flickers in a pattern that almost repeats, but never quite. Astronomers call these signals Quasi-Periodic oscillations, or QPOs for short. They are one of the closest things the universe gives us to a song from the deep. Picture a black hole with a dying star spiraling into it. As the gas from that star falls inward, it forms a flat, spinning disk of glowing matter. This disk is unbelievably hot, brighter than millions of suns, and it sings in X-rays. When we point our telescopes at these systems, we see the light rising and falling in rhythmic pulses. The pulses are steady enough to feel like a beat, yet loose enough to drift, wander, and shift. If you take the raw signal from one of these systems and shift its frequency down into the range of human hearing, something remarkable happens. You hear a low hum, almost like a distant engine. Sometimes it sounds like a purring cat, many light years wide. Sometimes it warbles, like a voice trying to hold a note underwater. This is not a metaphor. Researchers have converted X-ray timing data from real black hole binaries into audible waveforms, and the result is a kind of cosmic sound recording. The universe, of course, does not carry sound the way our air does. There is no medium between the stars to move in waves against your ear, but the light itself carries the rhythm, and rhythm is the deep bone of what sound really is. A pulse repeated, a pressure that rises and falls. Turn the pulse of a black hole disk into a speaker's motion, and you get something a human ear can finally hold. What creates these oscillations remains an open question. One idea suggests that hotspots on the inner edge of the disk orbit the black hole at dizzying speeds, and each time a bright patch swings around, we see a flicker. Another idea proposes that the whole inner disk wobbles, processing like a spinning coin about to settle. A third possibility involves standing waves in the gas itself, resonant modes trapped near the black hole, the way sound is trapped inside an organ pipe. Each theory fits some of the data. None fits all of it. The chorus in the deep still hides its source. The frequencies themselves range widely. Some QPOs pulse only once every few hundred seconds. Others repeat hundreds of times per second, so fast that they brush against the natural timescales of matter, falling through the strongest gravity we know. These fast pulses are called kilohertz, QPOs, and they seem to come from just above the surface of neutron stars, or from the very lip of a black hole. If we could stand there, unharmed, we might hear something like a shrill whistle above the low roar of the disk. Neutron stars have their own kind of music. When one experiences a sudden crack in its crust, a starquake, its whole body rings. The vibrations are almost too fast for imagination, thousands of ripples per second across a sphere only a few miles wide. These ringing modes have been detected in the fading X-ray glow of magnetar flares. Slowed down for human ears, they sound like a bell struck in a cathedral of pure iron. There is also the sound of the solar wind, which spacecraft have translated into eerie whooshes and hisses. The rings of Saturn, when their radio emissions are converted, sound almost like whale song pulsars. When their pulses are amplified, sound like a steady drumbeat that never tires. The universe, once thought silent, turns out to be full of rhythms just waiting for the right translation. The mystery worth sitting with tonight is that all these sounds are quasi-periodic in some sense. Even the pulsars drift, even the QPOs shift their frequency from night to night. Nothing in the sky repeats with perfect precision. Every cosmic rhythm has a wobble, a breath, a slight impatience. And this raises the same quiet question that runs through this whole episode. Is the universe built to keep perfect time anywhere? Or does every repeating thing carry a small imperfection that reveals something deeper about the fabric of time itself? Time crystals, if they truly break time symmetry in a stable way, might one day be the closest thing we have to a perfect beat. But even they, in the noisy real world, drift and decohere. Perhaps the song of the cosmos is meant to wander. Perhaps a rhythm without wobble would not be music at all. We do not know yet. We only listen and wander, and let the low hum from a distant disk carry us gently toward sleep. At the center of most large galaxies sits something enormous and quiet, a black hole with a mass of millions, sometimes billions of suns. And around these giants, matter falls in slow spirals, glowing as it goes. What is striking is that many of these cores seem to keep a kind of time. They brighten and dim on schedules that stretch across years, decades, even centuries. The math behind these rhythms is beautiful in its simplicity, though the deeper meaning of the rhythms is still an open question. Consider a small star wandering too close to one of these giants. If the star survives, it may settle into a long looping orbit, returning again and again to graze the black hole's edge. Each pass strips away a little gas. Each pass produces a flare of light. Astronomers have found galactic cores that flicker on cycles of a few hours, of days, of many years. The equations that describe these orbits are the same simple equations Kepler wrote down 4 centuries ago, applied to a much stranger stage. The elegance lies in the numbers. The period of an orbit depends only on the mass of the central object and the size of the orbit itself. Nothing else. Not the color of the star, not the temperature of the gas, not the age of the galaxy. Just mass and distance, joined by a simple power law. Double the size of the orbit in a certain way, and the period grows in a way you can predict on a single line of paper. This is why astronomers can watch a flare, time the next one, and confirm that a black hole of a certain mass is truly there. Some galactic cores pulse on timescales measured in minutes. These are called quasi-periodic oscillations, and their frequencies seem to lock into simple ratios, 3 to 2, 5 to 3, the kind of ratios that also appear in the resonances of moons and the harmonies of vibrating strings. Whether these ratios reveal something deep about how matter spirals into a black hole, or whether they are coincidences of geometry, remains unsettled. One idea says the ratios come from the natural frequencies of the disk of hot gas. Another says they come from the spin of the black hole itself, twisting space-time into a slow rotation that gas cannot help but follow. Then there are the slower pulses. Some galactic cores brighten and fade on cycles of years, as if a hidden partner were tugging at the disk on a wide, slow orbit. In a few cases, the math points to 2 supermassive black holes locked together, circling one another at the center of a single galaxy. Their orbital period, calculated from the timing of the flares, can be 12 years, or 50, or 200. Each prediction is a small act of faith in the equations, and when the next flare arrives on schedule, the faith is repaid. The distances involved are hard to hold in the mind. A single galactic core might sit 50 million light-years away, the light we see left before the first humans walked upright. And still the rhythm arrives cleanly, unblurred by that immense trip. This is one of the quiet gifts of the vacuum. Empty space keeps time for us, carrying the pulse across unimaginable gulfs without smearing it. The mathematics also lets us look backward. From the shape of a light curve, the graph of how brightness rises and falls, astronomers can work out the mass of the black hole, the size of the orbit, sometimes even the tilt of the disk. It is a kind of reverse music, hearing a rhythm and deducing the shape of the instrument. 2 centuries of careful astronomy have made these deductions possible. Simple equations, patient observation, and a willingness to wait for the next pulse. Whether these long, slow rhythms hint at something like a time crystal at galactic scale is unclear. A galactic core is not a quantum system in the usual sense. Its repetitions come from classical orbits and classical gas dynamics, not from the strange quantum behavior that gave time crystals their name. Yet the resemblance is quiet and suggestive. Both involve systems that return to themselves on a schedule. Both involve the strange fact that the universe prefers certain rhythms over others. Some thinkers wonder if there is a common language underneath, connecting the tick of a black hole disk to the pulse of a quantum lattice. Others suspect the resemblance is only skin deep, a coincidence of language rather than physics. The math, in either case, remains beautiful. Mass, distance, time. 3 numbers joined by a rule so simple it fits in a whisper. From that whisper, the long, slow song of the galactic cores. We have wandered through the pulsing of stars and the slow drum of galactic cores. And now we come to a stranger rhythm still, a rhythm so delicate that for many years most physicists believed it could not exist at all. The time crystal, a pattern that repeats not across space, like the atoms in a grain of salt, but across time itself. To understand why this idea sits on the edge of physics, picture an ordinary crystal in a snowflake or a sliver of quartz. Atoms sit at regular spaces. They break what physicists call spatial symmetry. Space in that small region is no longer smooth and featureless. It has a beat, a structure, a repeating step. In 2012, a physicist named Frank Wilczek asked a quiet question. What if something could do the same thing in time? What if a system could settle into its lowest energy state and yet still tick, still move, still repeat forever, without any push from outside? At first, most of his peers said no. It sounded too much like a perpetual motion machine, and those have been ruled out for a very long time. The balance here is astonishingly fragile. For a time crystal to exist, many small things must line up just right. The system must be quantum in nature, made of particles whose behavior follows the strange rules of the very small. It must be isolated well enough that heat does not creep in and blur its rhythm. It must be nudged gently and periodically by an outside pulse, and yet respond at a slower beat than the nudge itself. This last part is the heart of the trick. The crystal answers the drummer, but on its own time. Change any one of these conditions, and the whole effect dissolves. Warm the system slightly, and the delicate quantum order breaks apart. Nudge it in the wrong rhythm, and it either falls silent or heats up into a smear of noise. Let it talk to the outside world too freely, and the pattern fades like breath on cold glass. In this sense, a time crystal is a bit like Earth itself, a thin atmosphere, a narrow band of temperature, a precise arrangement of forces that no one demanded. And yet here we are. Experiments in the last several years have gently confirmed that these fragile states can be made. Small chains of ions held in traps of light and magnetic fields. Tiny defects in diamond, arrays of atoms cooled to near the coldest temperature possible. In each case, researchers have watched a system beat at half the rhythm of its driver, or a third, and hold that beat for a while before the world outside crept in and hushed it. These are not perpetual motion machines. They are not free energy. They are a subtle quantum arrangement in which the lowest state is not still. But here the deep question opens. Does this tell us something about time itself? Or is it a small quantum curiosity, beautiful but limited, with no message for the universe at large? One view holds that time crystals hint at a hidden structure inside time. If space can carry a repeating pattern, and time can too, then perhaps time is more like space than we thought. Perhaps our sense of a smooth flowing now is only one way of describing a dimension that can hold texture, rhythm, and shape. Some thinkers wonder whether the universe on the largest scales might carry echoes of this kind of temporal order, though no one has shown that it does. Another view is calmer and perhaps more sober. It says that time crystals are a lovely example of what quantum systems can do when carefully arranged, and nothing more. They break a symmetry, yes, but only under such controlled conditions that the effect may never scale up to anything larger than a laboratory sample. Under this reading, they teach us about quantum matter, not about the nature of time. They are a hint, not a revelation. Both views remain open. No one has built a large time crystal. No one has seen the effect stretch beyond the microscopic, and no one has ruled out the possibility that someday a bigger version might be found, or engineered, or noticed hiding inside some natural system we have not yet examined closely. For now, we can only sit with the balance, a pattern that persists because of quantum stubbornness, a rhythm that survives only when many delicate conditions align, a small clock inside cold atoms that may be trying to whisper something about the shape of time, or maybe simply doing what quantum things do, quietly, in the dark, on the very edge of what our physics can describe. We have wandered through many kinds of repetition tonight. The steady tick of a pulsar, the breathing of a swollen star, the slow return of a comet on its long dark loop. And now, near the end of our slow walk, we come to the largest question of all. What if the universe itself repeats in time? Not its contents, not its stars and moons and drifting dust. The universe, the whole thing, as a single vast oscillator. This is one of the oldest ideas in cosmology, and one of the least settled. Some thinkers, going back thousands of years, imagined that everything moves in great cycles. Worlds are born, worlds fade, and worlds return. Modern physics has not confirmed this picture. It has not ruled it out either. Instead, it has given us several careful competing versions of the idea and left the choice among them open. One version is called the cyclic model. In this picture, our universe is only the latest verse in a much longer song. Before the hot, dense beginning we call the Big Bang, there may have been another cosmos, cooling and stretching, just as ours does now. When that earlier universe grew thin and cold enough, some process reset it, and a new expansion began. If this is true, then time itself might be marked by great slow beats, each one lasting untold billions of years. We are living inside, one beat, unable to hear the ones before or after. A different version is called the bouncing cosmos. Here the universe expands, then slows and falls back on itself, then bounces outward again. Each bounce erases much of what came before, but leaves faint traces behind. Some researchers wonder if very small clues from a previous cycle might still be hidden in the cosmic background glow, the soft light left over from the young universe. Searches for such clues have turned up interesting hints and quiet disappointments in equal measure. Nothing is confirmed, nothing is ruled out. Set against these ideas is the more familiar view, sometimes called the one-shot universe. In this picture, there is no rhythm at all. The cosmos began once, expands once, and will simply keep thinning and cooling until stars burn out and matter itself grows quiet. Time, in this view, has a beginning but no repetition. The universe is a single long exhale, not a heartbeat. Many physicists find this picture the most consistent with current evidence. Many others find it incomplete, because it leaves the beginning itself unexplained. Between these two pictures sits a third, stranger possibility. Some theorists have suggested that even a universe that appears to run down forever might, on unimaginable timescales, reset itself through quantum accidents. A patch of empty cold space might, by the tiniest chance, arrange itself into something resembling a new beginning. If this happens, then repetition returns, but only across spans of time so long that the numbers lose all human meaning. Whether such events are truly possible remains a matter of careful argument. Notice what all of these ideas share. They ask whether time, at the largest scale, has a texture, whether the cosmos has a beat we cannot feel because we live inside a single note of it. This is the same question the tiny time crystals raised, only stretched to the size of everything. If time can have a periodic structure in a small quantum sample, could it have a periodic structure across the whole universe? No one knows. The mathematics that describes the small case does not simply scale up to the large one. Each level of nature seems to require its own careful listening. There are also skeptics who point out that we may be fooling ourselves. Human minds love rhythm. We hear it in music, in seasons, in the beating of our own hearts. When we look outward, we may be looking for a pattern that is not really there. The universe may not repeat. It may simply be once and slowly change, and that may be enough. This warning is worth holding gently as we wonder. What we can say is that the question is still open. The cosmic background glow has been mapped in fine detail, and it has not settled the matter. The equations of general relativity allow more than one solution, and they do not tell us which one nature has chosen. New instruments are being built. New ideas are being tested. Somewhere in the coming decades, a measurement may tip the balance toward one picture, or reveal that all our current pictures are too simple. For now, the largest oscillator, if it exists, hums at a frequency far below our hearing. We sit inside its one long note, and we listen, and we do not yet know if another note is coming. Imagine drifting forward through time, gently, as if borne on a slow current, not 100 years, or 1,000, but 1,000,000, and then 1,000,000,000. The sky above our world will not look the same. The stars we know by name will have shifted, drifted, some of them gone dark. And yet, if the deepest ideas about rhythm in the cosmos hold true, something will still be pulsing, something will still be keeping time. 1,000,000 years from now, most of the pulsars we listen to tonight will still be spinning. Their beats will have slowed by a tiny, patient fraction. The neutron stars themselves, those small, dense hearts left behind by dead suns, will have cooled a little more, but their signals will keep arriving on Earth, or on whatever remains of Earth, with the same steady discipline. They are among the most reliable clocks the universe has ever built. 100 million years from now, the sun itself will begin to change in ways we can already model. Its brightness will slowly climb. The oceans of our world may thin. The rhythms we count on now, the seasons, the tides, the yearly circle around the sun, will still repeat, but the stage they play on will look different. New continents will have gathered, mountains that do not yet exist will have risen and softened. The song of the solar cycle, that 11-year hum of magnetic breathing, will still be humming. Whether anyone will be here to hear it is a question no one can answer. Push further 5 billion years. The sun swells into a red giant, wide and slow and cool at its edges. Its old rhythm ends, but the galaxy around it keeps turning, and other stars, younger stars, take up the pulse. Cepheid variables, somewhere out in the spiral arms, are still breathing in and breathing out. Binary pairs are still eclipsing each other in patient shadow dances. New pulsars are being born from new supernovae, spinning up into fresh cosmic metronomes. The clocks change hands. The clockwork continues. And here is where the mystery deepens. Softly, if time crystals are more than a laboratory curiosity, if they hint at something structural about time itself, then the rhythms of the far future may not just be the rhythms of matter, they may be the rhythms of the medium that matter moves through. One idea is that time carries its own faint texture, and that every oscillator, from a pulsar to a quasar to a quantum experiment, is only tuning into that texture in a different way. Another idea, held by many physicists, is that time is smooth and featureless, and every rhythm we see is only ever a property of the thing doing the rhythm. Both views may still be alive 1 billion years from now. Neither may be settled by then. Zoom further still, 1 trillion years. The universe has expanded so much that most galaxies have slipped beyond each other's reach, each one adrift in its own dark bubble. Star formation is winding down. The bright blue giants are long gone. What remains are the small, slow, red dwarfs sipping their fuel across timescales that dwarf the current age of the cosmos. Some will pulse faintly in cycles we cannot yet measure, because we have not had time to watch them long enough. Their variability is a question waiting patiently for future eyes. Even further, in the deep future physicists sometimes call the degenerate era, the last stars fade to embers. White dwarfs cool into black dwarfs. Neutron stars slow. Black holes remain. Some ringing quietly from ancient mergers, their signals stretched into wavelengths so long they blur into the background, and still, if certain speculative pictures are right, the underlying quantum world beneath it all may keep ticking time crystals, or whatever the mature version of that idea turns out to be, might carry on their strange refusal to sit still, long after ordinary matter has forgotten how to shine. Whether any of this rhythm ever loops back on itself, whether the whole universe is one great oscillator, breathing out and someday breathing in, is a question no one can answer tonight. Some models suggest a slow, endless expansion, cold and quiet. Others allow for bounces, cycles, returns. The evidence is incomplete. The mathematics is still being written. For now, it is enough to picture the far future as a place where the clocks have changed, but the ticking has not stopped. New rhythms will replace the old ones. New oscillators will pulse in the dark. The universe seems less like a story with an ending and more like a piece of music that keeps finding new instruments. So let us step back now, all the way back, and look at what we have been circling for these many quiet hours. Structures that repeat in time, rhythms folded into the fabric of the universe. Signals that return and return and return again. Whether we are listening or not, there is something worth sitting with in that idea. The universe, as far as we can tell, is not a still photograph. It is not a single frozen moment. It moves, it pulses, it swings between states, and these motions happen across every scale we know how to measure, from the flicker of a quantum system to the slow turning of galaxies over billions of years. You are, in a very real sense, part of that rhythm. The atoms in your body were forged inside stars that lived and died long before the Earth existed. The calcium in your bones, the iron in your blood, the oxygen in every breath you take tonight, all of it was cooked in stellar cores and scattered by supernovae across the dark. That scattering was itself a kind of pulse, a single beat in a very long song. And here is the quiet wonder. The same laws that let a star pulse, that let a pulsar spin, that let a binary system dance in slow orbit, are the laws that let your heart beat. The same physics that governs the rhythm of a quantum time crystal governs the rhythm of the neurons drifting towards sleep inside your skull. We are not separate from the rhythms of the cosmos. We are one of them. What a repeating signal might mean, then, is something deeper than a curiosity in a distant observatory. It might mean that time itself has texture, that the universe does not simply flow forward in a smooth, featureless line, but folds and repeats and layers upon itself in ways we are only beginning to sense. Or it might mean nothing of the sort. It might mean that repetition is just what happens when matter finds a stable pattern, and that our sense of meaning is something we bring to the sky, not something we find there. Both views remain open, neither has been ruled out. Some researchers wonder whether the periodic structures we see, from the ticking of atomic clocks to the ringing of black holes, hint at a hidden geometry of time waiting to be understood. Others suspect that time is simply the stage on which patterns play, and the patterns tell us about the actors, not the stage. We do not yet know which view, if either, is closer to the truth. What we do know is that the universe seems at every level to keep time with itself. A neutron star sweeps its beam across the galaxy every few milliseconds. A Cepheid variable swells and dims across days. A comet returns after decades. A binary system spirals inward across millions of years. A galaxy rotates once every quarter, billion, and somewhere, in a small quiet laboratory, a chain of atoms flips between two states in a pattern that will not stop, because stopping is not what it does. All of these rhythms overlap. They ride on top of one another, like the notes of a chord held for a very long time. And you, tonight, are inside that chord. Your breathing, slowing now toward sleep, is part of it. The soft pulse in your wrist is part of it. The turning of the earth beneath you, carrying you gently around the sun, is part of it. You are not observing the cosmic rhythm from outside. You are one of its voices. Perhaps this is the quiet gift that these repeating structures offer us. Not an answer, not a resolution to the mystery of what time truly is. Just a reminder that the universe is not silent and it is not still. It hums, it breathes, it keeps returning to itself in patterns we can begin to hear but cannot yet fully understand. And when we cannot understand something, we are allowed to simply notice it, to let it exist without demanding that it explain itself. The pulsar will keep sweeping its beam whether we solve it or not. The time crystal will keep flipping whether we know what it means. The comet will return on its long, slow arc whether anyone is watching from the surface of the earth. The rhythm does not need us, but we, small and warm and made of stardust, are welcome inside it tonight and every night, whether we are awake to hear it or drifting somewhere softer. The universe keeps its steady, patient, unresolved time. We have wandered a long way tonight, following the soft pulse of things that repeat in time. Pulsars turning their lonely lighthouses through the dark, stars breathing in and out across thousands of years. Comets returning to the sun like patient old friends. And at the strangest edge of all, tiny quantum systems that seem to tick in a rhythm woven into time itself. The mystery we sat with has no answer yet. Time crystals are real. They exist in careful laboratory setups, in cold clouds of atoms, and in small chains of quantum bits. They tick without spending energy, without winding down, in a way that once seemed impossible, and still. No one is sure what they mean. Some researchers see a small technical curiosity, a clever loophole in the rules of matter. Others wonder if we have brushed the edge of something deeper, a hint that time, like space, might have a hidden grain, a texture, a structure we have not yet learned to read. We do not have to solve it tonight. That is the gentle gift of a question like this. It waits. It will still be here in the morning, and the morning after that, quietly turning in the minds of the people who study it. You are allowed to rest. Picture, for a moment, a small blue planet turning slowly in the dark. Its oceans catch the light of a single pale moon. Clouds drift across the seas in soft white spirals. On the night side, cities glow like scattered embers. The planet turns, as it has turned for billions of years, one quiet rotation after another. A rhythm older than any clock, a rhythm no one had to invent. Now let your mind drift outward, past the moon, past the other worlds of this solar system, past the slow orange face of a gas giant with its rings of ice, past the frozen edge where comets sleep in long, cold orbits, waiting centuries before they fall inward again. The sun becomes a bright point among many. The many become a soft river of light. You are looking down on the galaxy now, its arms sweeping in a great slow wheel, a turning that takes hundreds of millions of years to complete a single lap. Even at this scale, there are rhythms. Stars rise and fall in brightness. Black holes at the centers of galaxies flicker in patterns we are only beginning to understand. Waves in the fabric of space itself pass through us as we sleep. Gentle ripples from distant collisions that happened long before there were eyes to see them. The universe hums in a chord too deep for any ear. And on this small planet, in this small room, you are part of that hum. Your heart keeps its own quiet beat. Your breath moves in and out like the tide. Your body is made of atoms, forged inside stars that pulsed and shone and died long before the sun was born. You carry their rhythm inside you. You always have. The great question of whether time itself has a shape, whether it can be etched with patterns the way a crystal is etched in space, may take another lifetime to answer, or 2, or 10. The people who will finally understand it may not be born yet. That is all right. Every generation gets to hold a few beautiful open questions for a while, turn them gently in the light, and pass them on. For tonight, it is enough to know that the cosmos is patient. It does not hurry. It does not demand. It simply turns and shines and repeats and waits. The pulsars will keep pulsing. The stars will keep breathing. The comets will keep returning. The strange small time crystals in their quiet laboratories will keep ticking their soft, impossible tick. And somewhere, someone, someday, will look at all of this and see how the pieces fit. You do not need to be that person tonight. You only need to rest. Let the images fade. Let the questions soften. Let the slow wheel of the galaxy carry you gently toward morning. The universe is vast and old and gentle, with those who look at it kindly. There is a place for you in its long, quiet song. We may learn the answer in our lifetime, We may not, either way. The mystery is a kind of company, something to wonder about on nights like this. One when sleep is close and the dark outside the window is full of soft, distant light. Rest now. The rhythm will still be here when you wake. Subscribe for a brand new space topic every night. One tap and something incredible is waiting for you tomorrow. Sweet dreams.